In the last video, we saw some of the basics of working with sequences, how to generate terms, think about limits. We also saw examples of those that have closed form rules and those that have implicit rules, those recursive formulas, okay? Now we're going to go ahead and see some examples of how to actually generate these closed rules, these explicit rules, okay? It's not always easy. It may take a bit of creativity and ingenuity, but with enough practice, you might be able to see what to do. So let's go ahead and see. I have a sequence here. 1/2, minus 1/4, an eighth, minus a 16th. You can probably guess what the next term is. Yeah, that's right, 1/32. And what about after that? Minus 1/64. So our goal here is to find a closed rule for the general term, okay, a closed form rule for the general term an of the sequence, assuming this pattern continues. So let's think about what's happening here, okay? And I forgot to mention this in the last video, that usually, depending on the context, for here, we're going to start indexing our sequences at 1, unless otherwise you might index them at 0. So this is how you determine if someone knows how to write in Python or C or Java versus writing in MATLAB, where they count like normal people and start at 1. All right, so let's think about this here. Okay, let me go ahead and in blue here, I'll write these turn numbers. 1, 2, 3, 4, okay? And let's kind of brainstorm. Let's think about some things that are see here. So what do we see? Well, we see that the signs change. Okay. We have plus, minus, plus, minus, plus, minus. And we also see that the numerators are all 1. So numerator is 1. And the denominator, that's a hard word to say. Denominator is a power of 2. Right? Those of you who know your binary numbers, right? 2, 4, 8, 16, 32, 64. Okay. So now the question is, can we figure out what a pattern is? Well, yeah, I think we can. And in this sign change thing, let's also make another note here, okay? If the index of the term is odd, like we have here, 1 and 3, odd gets a plus, and even gets a minus, okay? So that's going to give us an idea of how to work with this, okay? So, by the way, an example of a sequence that changes sign every term is called an alternating sequence. We'll need that later on. Okay, so what's a good candidate here? Well, let's try to see how I can relate those powers of 2 with the term numbers here. Well, I know, okay, that 2 is just 2 to the 1. 4, well, that's 2 times 2, that's 2 squared. 8 is 2 cubed. 16 is 2 to the 4. Okay, so it looks like here, my term numbers, let me highlight these. These term numbers are going to be my exponents. Okay, so maybe we can guess. Let's write down what a guess is here. An is going to be 1 over 2 to the n. Well, that seems reasonable, except what's the only issue with this guess? This one doesn't have alternating signs, but our actual sequence does. So how do we account for that? Well, let's also think here. I know that -1 to the first power is a -1. If I square -1, I get a +1. If I cube -1, I get a -1. And -1 to the fourth power is a 1. So here's the idea. If I have an odd power, I want it to be correspond to a plus sign, and even power to a minus sign. So I need to shift everything back or forward 1 step. Okay? So try to convince yourself that the rule to use here is -1 to the n minus 1 over 2 to the n. You could also use -1 to the n plus 1 over 2 to the n, so long as the signs match. And does that work? Well, let's check. Well, a1 here, let's see, we have -1 to the 1 minus 1 over 2 to the 1. Well, minus 1 to the 0 is a plus 1. 2 to the 1 is 2. Okay. A 2. We have 2 minus 1 in the exponent there, and then 2 squared. Well, 2 minus 1 is a 1. Minus 1 to the 1 is a minus 1. Then over 4. Okay. Let's keep checking. Okay, just as a sanity check, we want to make sure our rule works here. We get these same terms, so 3 minus 1 up there. 2 cubed. We get a positive in the numerator, and in the denominator we get an 8. And I think you're probably convinced that this indeed works. Minus 1 over 16. So is that our rule? You bet. So this guy here is our rule. Or this one, doesn't matter. Okay, so let's make this a little more clear. Let's clean this up here. In fact, I'll put it here. All right. So an is equal to, I'll use the first one that I wrote down, minus 1 to the n minus 1 over 2 to the n. And that's our rule to generate the terms of that sequence. Okay, see how you have to be a little creative sometimes, right? Explore. Think about the patterns that you see, okay? Let's take a look at another one here, that next one. So, here we go. 3 over 16, 4 over 25, 5 over 36, 6 over 49. Do you think you know what the next term is? Try to see if you can figure it out. Okay, what do you see? Let's ask that question. What do you see? So let's make our list here. What do you see? All right, what do you see? Well, all the terms are positive, okay, and that might be an observation you can use, so they're all positive. Okay. And look at the numerators, 3, 4, 5, 6. The numerators all go up by 1, okay? Numerators go up by 1 at each step. And the denominator, well, 16, 25, 36, 49, those are perfect squares. We have perfect square denominators. Okay. But you see they're not starting at like 1. So let's go ahead and like make a note here. 1, 2, 3, 4. What's the relationship between the index there and the numerator? Well, 3 is 2 more than 1. 4 is 2 more than 2. 5 is 2 more than 3. Okay. Huh. Looks like we might be getting somewhere. So let's maybe make a guess here. So let's guess. Let's say my sequence an is, well, I know that the numerator here is 2 more than the index. And I at least know that my denominator is a perfect square, but the thing is, which square do I choose? Well, 16 is 4 squared. Okay, let's maybe make some educated guesses here. So 16 is 4 squared, and 4 is 3 plus 1. Okay. So try to relate it to the index there. 25 is 5 squared, and 5 is, well, 3 plus 2. Okay, 36 is 6 squared, and 6 is 3 plus 3. So what about in the denominator? We add 3 to the index number, and then we square that number. Okay, that's promising. Well, does that work? Indeed it does, okay? So let's kind of run through it here. A1, 1 plus 2 is 3, over 1 plus 3 is 4 squared, 16. Okay, that's a check. A2, you can see we get 4 over, oh, that should be an n plus, no, that's right, 2 plus 2, okay. 4, and the numerator, and then the denominator there, 2 plus 3 is 5 squared, 25, okay. A3, 5 over 36, A4, 6 over 49, and can you guess what the fifth term is? 7 over 64. Okay, so this is our rule. Okay, it just takes a little bit of creativity. Play around with it. See what things you can get. And make sure that you check your guess. Okay, check your guess. Make sure it does work. Okay, make adjustments based on what you see. Now, for recursive formulas, it's a little harder. There's a few ways you can go about this, okay? So let's take a look at this. Our first term is 2, a1 is 2, and to get our next terms, an plus 1, that's going to be 2 times an. All right. So what is this saying? To get the next term, we do 2 times the previous. Well, before we even do anything, let's explore, okay? Let's try to brainstorm. Let's try to get some ideas here. Okay, let's write out a few terms here. So a2, okay, a2, brute, is going to be 2 times 2. 2 times the previous term, that's 4, okay. a3, 2 times the previous term. 2 times 4 is 8. a4 is 2 times 8, which is 16. Okay, so it looks like the only thing that we're really doing at each step is multiplying by 2. And that's what the recursion says up there, okay? But how do we get a closed rule? Well, let's try to relate this to things that we know, right? So all powers of 2, okay? 2 times 2 is 4, okay? 2 squared is 4. 2 cubed is 8. Let's go ahead and write this here. 2 squared is 2. 2 squared is 4. Wow, I'm tired. 2 cubed is 8. 2 to the 4 is 16. And let's do one more. Okay. a5 is just 2 times 16. Okay, see how that gets slid in there? That's 32. And 2 to the 5 is indeed 32. So, do we have to guess as to what the rule is? Well, a guess here would be 2 to the n is our rule an. Okay, we're just getting powers. Okay. Well, 2 to the first power is indeed 2. 2 squared is 4. 2 cubed is 8. Okay. Looks like that we're going to be generating them all. Okay. Now, you can also do this another way by this process called unfolding. Okay, let's try to imagine this thing here. So let's say that I write down my general rule here. an plus 1 equals 2 times an. Okay. Well, let's say I want to go down another step, all right? Well, how do I do that? Well, I take this rule, okay, and even if I want to write it for the previous, I know an is just 2 times an minus 1. The next term is 2 times the previous. So what I'm going to do is replace an here with 2 times an minus 1. So let's fix that. 2 times an minus 1. All right. Well, I've gone down 2 steps, okay? The gap between n plus 1 and n minus 1 is 2 steps. Okay, so let me draw a little bit of a ladder here. N plus 1 and n minus 1, that's 2 steps. Okay, that's 2 steps. And how many 2's are there so far? Well, there's 2 2's. You have 4. Let me write it like this. 2 squared times an minus 1. Can I go back another step? You bet. I can certainly go back another step. Okay, so if I go down another step, I have 2 squared times, what is an minus 1? It's 2 times an minus 2. an minus 2 is 3 steps from n plus 1. I have 3 2's. So I can inductively continue this procedure. Okay, you can actually prove this by a process called induction. My computer science folks probably know this at this point already. Okay. And you can figure out that the general rule here will get 2 to the n plus 1 if you unfold enough. Okay, if you unfold enough, you might be able to see this, okay? But our guess that we had here is indeed correct, that an is equal to 2 to the n. Okay, that's our function of n. Okay, now this next one's going to be a little trickier. Okay, we might need to figure out a bit more ways to get some insight for this one. So we're seeding at 2 again still. a1 is equal to 2. And our rule is as follows. The next term, an plus 1, is equal to the index of the next term, n plus 1, times the previous term, an. And then we're going to divide that by 2. We're going to take half. All right. Well, the best thing to do is to just explore. Okay, let's just explore. Let's see what these things look like. See if we can figure out what this pattern is. Okay, so let's look at a2. Well, that's going to be the new index 2 times the previous term 2 divided by 2. Well, 2 times 2 is 4, divided by 2 is 2, so we just get a 4 there. Okay. Now what about A3? We take the next index. Here, the next index is 3. Okay, take a look here. Let's do some coloring here. That corresponds with there, this with here. And then we take the previous term. In this case, previous term was 4. Okay, we're just putting that there. And then we're going to divide by 2. Well, 3 times 4 is 12. Half of that is 6. Okay, and I don't know why that's not right. That should be a 2, sorry. That should be a 2, and that should be a 3. Okay, Sean can't count today. All right, A4. Okay, we take the new index, which is 4, so let's do some color coding there. New index is 4. The previous term, 3, okay? And then we're going to take half of that product. 4 times 3 is 12, divided by 2 gives me 6. Okay, nothing really seems obvious yet at this point. Okay, you might be thinking, well, I think I've seen this pattern before. Well, careful, careful. Okay. A5. Okay, 5 times 6 over 2. Okay, we'll do some more colors here. Okay, happy little highlights. Okay, that turns out to be the wrong color, and that is 15. Okay, 2, 2, 3, 6, 15 doesn't really seem like anything yet. Okay, one more just for good measure. Okay, one more just for good measure. A6. Okay, we'll have 15. Nope, sorry. A6 we will get. Let's see here. 6 times 15. Okay, do our matching here. And then we're going to divide by 2. That's the wrong color. Okay. Well, half of 6 is 3. 3 times 15 is 45. Okay. But it doesn't really look like we're getting anywhere. But this is the place to start. Just start out by writing terms. See what maybe you can expect. Now, this is where this unfolding idea probably comes in. Okay, so let's go ahead and think about that for a second. Okay, so we have an plus, let's actually start off like this. Let's say I want an, okay? If I want the nth term, well, I'm just shifting down one index here, okay? I'm going to take the index here, n, times the previous term, an minus 1, divided by 2, okay? All right. Well, I know what an minus 1 is, okay? Remember, this rule here, let's do the highlighting again. This rule tells me how to get the next term from the previous term. It gives me that relationship. So now what are we going to do next? I'll write this n over 2. And then at an minus 1, I'm going to go ahead and replace that with what it should be, okay? Okay, so an minus 1, we take the index, n minus 1, put some parentheses there. Then the previous term, which in this case is an minus 2 over 2. Well, I have an n and an n minus 1. I have two 2's down there. Okay, let's just keep going. Okay, if I continue here, we have n times n minus 1. And on the bottom, I'll just smash those two 2's together into 2 squared, a lot of 2's there. Okay, an minus 2. Well, we take the index number, n minus 3, times the previous term, divided by 2. And I just realized that should be n minus 2 and then n minus 3 there, sorry. Okay, let's make this correct. There we go. Everything's fine. Now, how many 2's do I have total on the bottom? I have 3. I've gone back 3 steps. So let's go ahead and make this clear here. N times n minus 1 times n minus 2 over 2 cubed. I have an minus 3. And how many steps have I gone back? 3 steps, 3 2's. You can probably see it, right? If I go down 4 steps, I'll get 4 2's, 5 steps, 5 2's. And how many of those factors do I have in the numerator? 1, 2, 3. Because I've gone down 3 steps. Now, let's do one more. just to drive the point home, okay? Just to drive home. N times n minus 1 times n minus 2. Now from the an minus 3, I'll have an n minus 3 join the party. I'll have an extra 2 join the party on the denominator. And I have an an minus 4. Okay, you see what's happening here? Okay, 4 steps down, 4 2's. Now, if you continue in this fashion, okay, if you continue, what do you get? Well, it turns out you'll get the following. N times n minus 1 times n minus 2, multiply all the way down to get something that you know, 3 times 2 times 1 over 2 to the n. Okay, I've gone down n minus 1 steps. Okay, n minus 1, that gives me a1, but a1 is 2. a1 is 2. Okay. Now, this number on top here, if I multiply from an integer and go all the way down to 1, multiply everything in between, we call that the factorial. That's n factorial on the numerator divided by 2 to the n minus 1 times a 2. And it looks like what we have here for a closed rule after canceling some exponents here is n factorial over 2 to the n minus 2. So this one was a little harder, okay? That one was a little harder. Okay, so let's make a definition down here, okay? Because we'll be seeing this symbol a lot, okay? N factorial, we're not just shouting it to the heavens. We take the number and multiply by everything down until we get to 1. Okay, so for example, okay, 4 factorial, 4 times 3 times 2 times 1, blast off, that's 24. And 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1 is 50, 40. Okay, we're going to be seeing this factorial come up a lot. Okay, but this unfolding idea you can take and use that to play around to get some close rules. Okay, so that concludes our little exploration with how to get some of the basics down and how to write some rules. We saw some easy examples and some tricky examples. And now we're going to go into some of the meats, okay? We're going to develop some vocabulary for how to talk about sequences. And I'll see you in the next one.